Good evening. Welcome to today's live discussion session for the NPTEL course Water Supply Engineering. I am Reshma R, Research Scholar from Department of Civil Engineering, Hydraulics and Water Source Engineering Division, IIT Madras. I shall wait for 2 more minutes and then start the today's session. During the session, I shall keep my video off so that uh, internet glitches can be minimized at my end. Okay, I shall share my screen now. Please let me know whether it is visible for you.
Yes, it is visible.
Okay, thank you. So we'll start by 7:05 so that if anyone is waiting to join, can join as well. Okay, I think we'll start the session. Okay, all right. So, first question for today's discussion is the criteria for selecting water source include option A long term availability of good quality of water. Option B distance of source from the center of water consumption. Option C cost of water abstraction from the source and transmission to the treatment facility. Option D all of the above. So, what is the criteria for selecting a water source? What is the criteria that we select a water source as a best fit for that particular city? You can put in, like, you can type in your answers in the chat box. So we have option A as long term availability of good quality water. Option B regarding the distance of source and water consumption center. And the third one is regarding the cost. So, which is the criteria for selecting water source? All right, so we'll see what is the answer. Yes, correct answer is all of the above as you have answered. So, what are the criteria for water source selection? That is, when we plan to develop or design a water distribution network for a city or a place, the first thing we need to know is the demand, that is the requirement that we saw in the earlier classes. That how we calculate demand, what all factors are to be considered while calculating demand, all these things we considered. Now, once we know the requirement of the city, the next thing to select is the source of water. Which one is best suited for that city is to be identified. So, for that, we have certain criteria. Where first one is characteristics of source or sources of water and water itself. Second one, regional geographic properties. Third one, feasibility for stage wise development. And fourth one, economics and cost. So these four factors are to be always considered while selecting the water source. Sorry, I think. Um, did you lose my screen sometime in between? Or was it visible? Okay, I think my screen have been lost. Sorry for that. Yeah. Is it visible now?
Yes, ma'am.
Okay.
Screen is visible.
Yeah. So we were talking about the criteria for selection of water source. So it depends upon the characteristics of the source as well as the water. The next one is the regional geographic properties, which will differ from place to place. Third one is the feasibility for stage wise development. And fourth one is the economics and cost. Now we'll see one by one. So the first one is characteristics of source of water and water itself. So first thing we need to check upon is the characteristics or the quality of water source as well as the water available. It includes availability of water, that is the quantity available, general longevity of the sources, that is whether it is available for a short term or whether it is available for a long term. The next thing is water quality. Is there any issue? I think someone had unmuted. Sorry again, one like internet issue was there here. Sorry for that. Okay. Yeah. So yes, so we were talking about the characteristics of sources of water and water itself. So it includes the quantity available as well as the longevity of the sources. Longevity of the sources indicates the term over which the water is available, whether it is a permanent source or a temporary source. If it is a temporary source, whether it is short term or long term availability is there, all those factors we have to consider. And the water quality, which is the very important, like most important factor to be considered, is water quality. When it comes to quality, when we check the present quality status of the water, we need to make sure that the water won't be polluted in the future as well. That is the fourth point, that is potential for future pollution. Even though the water is fit for drinking or domestic purposes in the present status, we should ensure that it will be the same in the future as well. That is, it should not get polluted in future. And the last one is access to the source. So we should be able to reach up to the source so that we can uh, take as much as water we need to the required consumer point. So this is the first factor or first criteria that we consider while we select source of water for the water distribution network. Right. Now, second characteristic is the regional geographic properties. So, the regional geographic properties include distance of source from the center of water consumption, availability of natural or man made water storage capacities, availability of any nearby elevated terrain, nature of soils to be used for installing water conveyance. So this is like the regional geographic properties include all that is related to the site specific conditions, that is geographic conditions. For example, if we have an elevated terrain in the nearby vicinity, we can make use of it to put our storage tank so that the water supply can be enhanced merely by gravity flow. Similarly, we need to check the distance of the source and the consumer point. Lesser the distance, lesser is the requirement for conveyance system, so lesser the cost. Moving on to the next criteria for selecting the water source, that is feasibility for stage wise development. Feasibility study means we have to assess whether a proposed source of supply is likely to be a success or not. That is, we have selected a source. Now we need to make sure that this will be a success. So we need to conduct a feasibility study. That is in in each stage or stage wise development whether it is feasible or not. That we have to assess. The last criteria is economics and the cost. Obviously, though all the three other criterias are met, if the cost of construction and maintenance exceeds our available budget, we may not be able to go forward with the source of supply. So we may have to change that particular source of supply. So economics and cost as well plays a role in deciding the source of water for the water supply system. Now, having seen all the criteria for selecting water source, we'll see which all are the sources of water for public water supply. First set of source is surface water sources, which include springs, lakes, ponds, rivers, reservoirs, estuaries, and wetlands. Second set, we have the groundwater sources like alluvial aquifers, rock fissures water, karstic water systems, artificially recharged groundwater, and groundwater drawn indirectly from surface water. Also, we have atmospheric water in the form of rain and storm water. We have recycled wastewater. We have brackish or saline waters. So, among these atmospheric water, every one of you knows it's rainwater or storm water means that comes as precipitation from the atmosphere down to earth. That is what is called as rainwater and storm water. Recycled wastewater is nothing but the water that is recycled after the first use and is again provided for reuse. Usually, the recycled wastewater is used for flushing, for gardening purposes, etc. The third one, that's brackish or saline water, is the water from Ocean we have, which we desalinate and then supply. So the first sets, that is surface water and groundwater, we'll see what is that one by one. First, we will go through each of the surface water sources and then we'll check on the groundwater sources. So the first surface water source, that is spring. What is spring? They are natural exit point at which the groundwater emerges out of the aquifer and then they appear on the earth's crust, top of the earth's crust, to become surface water. So springs are actually groundwater that is emerging at a particular point on the ground surface to form surface water. So it is a part of the water cycle as well as the hydrosphere. And this emerging of water at the exit point happens due to many natural forces. That is, for example, it may be gravity or sometimes hydrostatic pressure. But the forces are purely natural. Some natural forces acts on that groundwater and thus it gets immersed at the exit point, forming the surface water. The second surface water source, that is lake. Lakes are also naturally occurring. They are relatively larger water bodies but completely surrounded by dry land. It will be the boundary will be dry land, and the flow will be much slower than any inflow or outflow streams that serve to feed or drain it. That means it will be having very less flow rate when compared to the feeder or draining streams, and they lie completely on the land and they are not connected to the ocean like rivers. Rivers have a connection to oceans, but lakes are completely bounded by dry land. And we have freshwater lakes as well as saltwater lakes, and these saltwater lakes can have salinity even higher than that of seawater. Going on to the third natural third surface water source, that is pond. A pond is a small, still, land based body of water, and that is formed by pooling inside a depression either naturally or artificially. So, earlier told springs and lakes, they were naturally occurring and they had some flow, but when it comes to the ponds, they can be made either naturally or artificially. But the fact is that the water will be still and it will also be bounded by dry land. The next one, the rivers, they are natural flowing water course, usually freshwater stream. They may flow over the surface of the earth or may cave towards another water body at lower elevation. That is, for example, it can join an ocean, it can join a bay, sea, wetland, or even another river. Then we call it as tributaries, major river, etc. And during its course of time, it may even get dried, it may flow into the ground as well. And if the rivers are small, they may be called as creek, brook, or rivulet. The next surface water source, the reservoir. Reservoir is actually the enlarged lake that we see behind the dam. It can be a man made structure constructed to store water or maybe a naturally occurring formation. The next one is estuaries. Estuaries are actually partially enclosed coastal body. There is one side it will have the brackish water from ocean, and the other side it will have the inflow from the river or stream. Thus, it can be considered as a meeting point of river or stream with ocean. Maritime environments and river environment conjunctions. These are example of an ecotone or estuary. So estuaries are always having one side brackish water and the other side fresh water from a river or a stream. The next one we have is the wetland. Wetlands are ecosystems with fresh or brackish water. It can be fresh water, it can be brackish water, as we saw in the case of lake. This can be a permanent covering or a temporary covering of water over the soil. Temporary in the sense it can be seasonal depending upon the weather or climate. For example, it may be like it may exist only during monsoon season time at times. Now, according to the Article 1.1 of Ramsar Convention, which is an intergovernmental convention on wetlands, wetlands are defined as marsh, fen, peat, and or water, whether natural or artificial, permanent or temporary, with water that is static or flowing, fresh, brackish, or salt, including even the areas of marine water, the depth of which at low tide does not exceed 6 meter. So this is the exact definition for wetland according to Ramsar Convention. That is, it can be either natural or artificial. It can be either permanent or temporary on a seasonal basis. The water contained in the wetlands can be static or flowing. It can be fresh water or brackish water. So it has a wide definition. We have wide definition for wetland. Next one, that is the groundwater source, alluvial aquifer. Alluvial aquifers are the aquifers that have unconsolidated material or alluvial material which is deposited by the flowing water, and this typically occurs near to rivers or buried paleo channels. Generally, it is composed of clay, silt, sand, gravel, or other alluvial materials, which are usually deposited by the running water of a stream or river. The next one, rock fissures water. It is the groundwater circulating in fissures or gaps of hard erupted sedimentary rocks. Examples for sedimentary rocks are limestone, sandstone, quartzite, granite, etc. So, if they have a long, deep cut, and if groundwater circulates through that, that is called rock fissures water. Next, we have the karstic water systems. These are actually network of interconnected fissures or fractures or cracks, and they will form a conduit, pipe like conduit with low permeability, low rock matrix. And most of the cases, the groundwater flow occurs through these kind of network of fissures or through karstic water systems. Then we have artificially recharged groundwater. That is, if the groundwater potential is very low, if the groundwater potential or our available groundwater cannot meet the requirements, we may even artificially recharge the groundwater. There are various means for that. For example, we can redirect the water across the land surface through canals so that it may infiltrate. We can provide artificial infiltration basins or ponds where we allow the water to stay still and allow it to infiltrate slowly into the ground. We can use irrigation furrows or sprinkler systems so that directly water reaches the ground surface or the root zone without much loss in through evaporation and all. Or we can use injection wells. Injection wells are nothing but the wells where we directly inject water into the subsurface through these wells. We directly apply water into the subsurface. So these are the different sources. Last one is groundwater drawn in directly from surface water. That is, we have seen so many surface water sources, either by due to infiltration or other gravity flows. This surface water can go deep into the infiltration, percolation, etc. The surface water can go deep into the groundwater directly. So these are the different sources of water, and we saw the criteria for selecting the best suited source of water for each particular case. Now we'll move on to the next question. Question number 2. For surface water intake, the common type of shape provided for water entry through the inlet pipe of raw water from collection unit is option A, concave type entry, option B, bell mouth entry, option C, flat type entry, option D, none of the above. So, which is the common shape adopted for, which is the common shape that we adopt for water entry through the inlet pipe of raw water in the case of surface water intakes? You can type in the answers in the chat box. Okay, we'll see the answer. Yes, option B, bell mouth entry. So generally, bell mouth entry, that bell mouth shape is provided for surface water intakes. And in order to prevent entry of trash or any other material into the intake structure, we'll provide a fine screen at the bell mouth. So moving on to the third question. River intakes, if situated in a navigation channel, are protected by option A, providing a wire mesh on intake inlets, option B, constructing a sufficiently deep intake foundation, option C, constructing a cluster of piles all around the intake, option D, all of the above. So if we are having a river intake in a navigation channel, how can we protect that particular river intake? So, is it A, B, C, or all of them? Okay, we'll see what is the answer. Correct answer is option C, constructing a cluster of piles all around the intake. So, if we are putting our intake in a navigation channel, then we need to construct piles all around the intake so that that particular intake is protected from the incoming barges or ships. So there are certain criteria for the positioning and construction of intakes. That is, intake should not be constructed in a navigation channel as far as possible, because there is chances for wide disturbances that may happen in the water as well as the sediment deposits or suspended sediments because of the movement, in and out movement of the ship, barges, etc. So, as far as possible, we should avoid construction of intakes within a navigation channel. Second thing is that if it has to be constructed, it should be protected by a cluster of piles all around from forces caused by moving ships and steamers. That is what is the answer for this particular question. That is, it should be protected firmly by constructing piles all around. Then option A was strainers in the form of wire mesh. This actually we provide on all intake inlets so as to avoid entry of large floating objects and fishes. So, in order to prevent the entry of these fishes or any trash or other unwanted objects into the intake, we usually provide wire mesh, and this we provide on all kind of intakes. Then the another option there, the second option was provide sufficiently deep intake. But this is actually provided to avoid overturning of structure. This particular thing, that is the depth is increased or sufficiently deep intakes are provided so as to protect that intake structure from overturning. All right. Moving on to the fourth question. For a pumping well with discharge of Q, the drawdown SW is given as SW is equal to BQ plus CQ square. In this equation, option A, B is aquifer loss coefficient and C is well loss coefficient. Option B is well efficiency and C is well loss coefficient. Option C, B is well loss coefficient and C is well efficiency. Option B is well loss coefficient and C is aquifer loss coefficient. So what does the B and C in the drawdown equation stands for? So what does B and C in the drawdown equation represent? Okay, we'll see the answer. I don't have any answers in the chat box yet. Mm, okay, we'll see the answer. So the correct answer is option A. B is aquifer loss coefficient and C is well loss coefficient. So in the drawdown equation, SW is equal to BQ plus CQ square. We have SW is the drawdown obviously. B is the aquifer loss coefficient. C is well loss coefficient. Q is discharge. BQ represents aquifer losses. CQ square represent well losses. So the drawdown equation is drawdown SW is equal to sum of aquifer losses BQ plus well losses CQ square. Okay. Question number 5. For a pumping well located 100 meter away left to a river, net drawdown is estimated by superimposing drawdown due to discharge well with drawdown due to dash having same pumping rate. So we have a river, 100-meter left to that, we have a pumping well as well. So in order to determine the net drawdown in that particular pumping well, using superimposition principle, drawdown due to discharge well is superimposed with the drawdown due to what kind of well having same pumping rate? Option A, image discharge well located 100-meter away on right side to the river. Option B, an image discharge well located 100-meter away on left side to the river. Option C, an image recharge well located 100-meter away on left side to the river. Option D, an image recharge well located 100-meter away on right side to the river. So first thing is whether that image well is discharge well or recharge well. Second thing is whether it is to the left or right of the river. The pumping well that we're considering is to the left of the river. Then what kind of well do we consider during the superimposition principle application? Whether it is a recharge well or a discharge well, whether it will lie towards the left or right. You can type in the answers in the chat box. Okay, we'll wait for another 1 minute. Let everyone think and answer. Okay, we'll see what is the correct answer. Yes, correct answer is option B. That is, we will consider an image recharge well located 100-meter away on right side to the river. So our pumping well was to the left side. So pumping well is a discharge well. So the considered well should be an image recharge well and it should be on the right side at equal distance as the pumping well. So for an aquifer bounded with a recharge boundary, for example, river, here in this case it is a river. So river is a recharging boundary. Then we should consider imaginary recharging well with the same pumping rate as well as the same distance, and that should lie on the opposite side of the real considered well. Okay, hope that is clear. Moving on to the next question. In transient state analysis, for a given discharge, the drawdown due to a pumping well in a confined aquifer is considered as a function of option A location, option B time, option C both location and time, option D neither location nor time. So in the case of transient state analysis, What is the equation for drawdown you need to think of, and then you will get to know whether it is a function of location or time, or both location and time, or it is independent of location or time. So what is the equation for the drawdown due to a pumping well in a confined aquifer according to transient state analysis? Okay, we'll see the answer. Correct answer is option C, both location and time. So transient state implies that drawdown is a function of location and time. In reality, many aquifer tests will never reach the steady state. Sorry. And cone of depression will continue to grow over time. So, according to the transient state analysis, by Thies or non equilibrium equation, we have dou square h by dou r square plus 1 by r dou h by dou r is equal to s by t dou h by dou t, with h at r comma t equal to 0, that is initial state is h naught, and h when r tends to infinity and at time t is also equal to h naught. Here, capital S represents the aquifer storativity, small letter r is the radial distance from the pumping well, t is the time since pumping have started, capital T is transmissivity, and u is a dimensionless constant. So we have h0 minus h as q by 4 pi t integral u to infinity e raised to minus u by u du, where u is given by r square s by 4 tt, and that integral is known as the well function w of u. So if we substitute that value, we have h0 minus h according to Thies or non-equilibrium equation as q by 4 pi t w of u, and capital S as capital S is a storativity, that as 4t ut by r square. Moving on to the next question, question number 7. Which of the following type of pumps require priming? Option A, rotary pumps. Option B, centrifugal pumps. Option C, reciprocating pumps. Option D, all of the above. So, which of the following type requires pumping? Sorry, priming. This you might be even doing at home as well sometimes. So, in which type of pump do we need to do priming? Okay, let's see. Yes, correct answer is option B, centrifugal pumps. So the centrifugal pumps and jet pumps, another type of pump, they're actually Either put underwater, for example, you might have seen inside the wells we may place a pump, or it should be pumped, or it should be primed before it starts. That is, before it pumps water, that pump is to be primed, whereas rotary and reciprocating pumps do not require priming before first start. Now, what is priming? This is actually needed for centrifugal pumps and jet pumps because they almost have no suction power. So it needs the user to introduce the fluid whichever it is going to pump. It can be water or any other thing. In our case, it is water, in the water supply system. So we need to introduce fluid into the pump to improve the sealing of the pump parts on starting and to expel air from it. Now, if we are not doing priming, it will start sucking the dirt or soil beneath the water as well. It will like air will be there inside the pump parts. So to avoid that, we need to introduce that particular fluid which the pump is going to pump up. Okay. So that particular process is termed as priming, and this is required for centrifugal pumps and jet pumps, and these are not required for reciprocating pumps or rotary pumps. Moving on to the eighth question. An aquifer bounded on both above and below by impervious strata where groundwater is restrained under pressure is known as option A, confined aquifer, option B, unconfined aquifer, option C, leaky aquifer, option D, idealized aquifer. So there is an aquifer which is underlain and overlain by impervious strata, and hence the groundwater is restrained under pressure within the aquifer. What kind of aquifer is that? Is it a confined aquifer, unconfined, leaky, or an idealized aquifer? Okay, so I think most of you know the answer. Yes, it's option A, confined aquifer. So, confined aquifer is an aquifer that is underlain and overlain by impervious strata, restraining the groundwater under pressure. Now, we have different types of aquifers, that is confined or pressure or artesian aquifer, unconfined or phreatic aquifer, perched aquifer, and leaky aquifer. So we'll see one by one. So as we saw, confined aquifer or pressure aquifer or artesian aquifer is the one that is bounded both above and below by impervious strata, and the groundwater within this confined aquifer will be restrained under pressure. Unconfined or phreatic aquifer is the one that is bounded by a free surface at the upper boundary, and that free surface of water forms the water table or phreatic surface with water occurring at atmospheric pressure. So there is no pressure. It's not confined under pressure. It's free to atmosphere. Next we have perched aquifer. This occurs whenever a groundwater body is separated from the main groundwater by a relatively impermeable stratum of small aerial extent as well as by zone of aeration above the main body of groundwater. So it will be actually separated from the main groundwater body. It will be like a separate formation with very small quantity of water, that is perched aquifer. Then we have leaky aquifer. Leaky aquifers are actually, as the name says, it is having some leak either inwards or outwards. So it is overlain or underlain by semi pervious aquitard or semi confining layer, so that there is some loss or gain of water happening through the adjacent layers. Now we have different types of geological formations as well. So far we saw the different types of aquifers. We have other geological formations, namely aquitard, aquiclude, and aquefuge. So we'll see what is the difference between each of them. Okay. So aquifer is actually a formation that contains sufficient saturated permeable material to yield significant quantities of water. That is, aquifers will contain good quantity of water as well as it can transmit good quantity of water. These are generally aerially extensive and may be overlain or underlain by confining or impervious bed, as we saw, depending upon the uh, like mode of confinement. We earlier classified them as confined aquifer, unconfined aquifer, etc. So the next one is aquitard. Aquitard is also actually saturated. It also contains sufficient amount of water, but permeability of the layers are very less, so it will restrict the groundwater movement. It does transmit water, but the rate will be very low. That is, it does not yield water freely to wells, but within the aquifers, like from one aquifer to another, at very slow rate, it can transmit water. For example, sandy clay. The next one is aquiclude. Aquiclude is also saturated, but it is impermeable. It won't transmit any good quantity of water, neither in the wells nor among the aquifers. Example is clay. Then we have aquefuge. Aquefuge is actually impermeable formation. It doesn't have water and it cannot transmit water. For example, solid granite. I hope that is clear. So we saw like different types of geological formations, that is aquifer, aquitard, aquefuge, and aquiclude. And we saw different types of aquifers: confined aquifer, unconfined aquifer, perched aquifer, and leaky aquifer. All right. Moving on to the ninth question. Currently, the most common conveyance system for water in water supply projects is option A, pressure pipes, option B, open channels and flumes, option C, gravity tunnels, option D, aqueducts. So, which is the most common conveyance system for water in water supply projects that we adopt today? Okay, I have got answers as option A. Yes, correct answer is option A, pressure pipes. So, currently, pressure pipes are the most common and they have nearly eliminated open channels, aqueducts, and tunnels. So, The issue with open channels and aqueducts are that evaporation losses can be very much, theft can be more, and with the case of tunnels, the problem is difficulty in installation, high initial cost. So all due to all of these reasons, pressure pipes have become common these days, and we have many materials that can be used for construction of these pressure pipes depending upon the type of water flowing through it, whether it is fresh water or wastewater. Depending upon that and depending upon the requirement, there are different types of materials used for the construction of pressure pipes. For example, cast iron, steel, galvanized iron, copper, are common, PVC, asbestos cement, and concrete. But recently, asbestos cement have been avoided from the list because of the cancer causing elements in that. So now we are using mostly PVC pipes. Then concrete, large concrete pipes are there for wastewater supply, this thing and all. Then we have steel and cast iron. So asbestos cement have been is being avoided these days. Okay, moving on to the next question. It's a numerical problem. The specific retention of a soil strata with a porosity of 0.34 and a specific yield of 0.19 is option A 0.34, option B 0.81, option C 0.53, option D 0.15. So we are given the porosity as well as the specific yield. We are asked to determine specific retention. So I'll give you 1 minute for the calculation. So what is the specific retention? It's very simple. Okay, so we'll see the answer. Yes, answer correct answer is option B 0.15. Two of you had answered correctly. Okay. So given porosity N is equal to 0.34, specific yield is equal to 0.19. Now we know that porosity is equal to specific retention plus specific yield. So specific retention is equal to porosity minus specific yield, that is 0.34 minus 0.19, which is equal to 0.15. So we were given the values of porosity and specific yield, and we know that porosity is the sum of specific retention plus specific yield. All right. Hope it is clear. Yeah. So, okay. So there is some mistake in this slide. Yeah, just now I found. Can any one of you point out that? Like I see many of you are not even interacting. So can I know what is like what have gone wrong in this slide? Can anyone type in the mess in the chat box? Something is wrong in this particular slide, number 35.
So porosity equal to volume of void by total volume.
Yeah, exactly. Okay, so at least I could see some interaction. Thank you. So I don't know. I don't know any other way to make you people interact, because even if I'm asking to type in the answers, I find only at max two per people will reply. For, till now, only two, and at times another person, like maximum three, had given me answers. Okay, so thank you. So now I'll change it to correct one. Yes. So can I know what is the particular definition I had written? What does that refer to? That is ratio of volume of voids to volume of solids. What is that? What is that term?
That is void ratio, I think.
Yeah, it is void.
Void
Yeah, yes, you are correct. So void ratio is basically the volume of voids by volume of solids, and porosity is volume of voids by total volume. Okay, thank you. So, yeah, so in this question, we had three terms: porosity, specific retention, and specific yield. So, porosity, as our friend told, it's ratio of volume of voids to total volume. Now, what is specific retention? It is the water that is retained by molecular attraction against gravity. That is, it is that particular amount of water that is there in the voids of soil which is retained against gravity, basically by molecular attraction. That is specific retention. And specific yield is the amount of water that can be yielded or drained from the aquifer under the influence of gravity. So both of these water is occupied within the pores itself. That is why the sum of specific retention and specific yield will together form the porosity of that particular aquifer or the soil formation. Hope that is clear. Moving on to the 11th question. Question number 11. Match the types of raw water sources with appropriate examples. In the first column, we have different types of water sources like groundwater source, atmospheric source, unconventional source, and surface water source. In the next column, we have lake, aquifer, rainwater, and recycled wastewater. So, which is the correct match? Option A1, B4, C3, and D2. Option B, A1, B3, C2, and D4. Option C, A1, B3, C4, D2. Option D, A2, B3, C4, and D1. Okay, I have got two answers. Is option D. Yes, correct option is option D, A2, B3, C4, and D1. That is, as we saw earlier, spring, lake, pond, river, reservoir, estuaries, wetlands all form surface water sources. So our lake is surface water source. Then we have alluvial aquifer, rock fissures, Karstic water system, artificially recharged groundwater, etc. comes as groundwater sources. The rain and stormwater consists of atmospheric water source, and recycled wastewater is basically unconventional source of water supply. Okay. Now, for questions 12 to 14, answer the following sub questions. For a raw water withdrawal and transmission unit is to be set up for flow of 3.5 meter per second. So we are going to set up or design a raw water withdrawal and transmission unit, and the flow requirement is 3.5 meter cube per second. The first question, that is question number 12, is the raw water transmission pipe diameter required to ensure approximate flow velocity of 2 meter per second. So we have the flow requirement as 3.5 meter cube per second. We have the required flow velocity as 2 meter per second. Then what is the required pipe diameter for the transmission line is the question. There is no options, it's a numerical type. So please type in the value of the diameter required in meters. So I'll give you 2 minutes for that. I think that is sufficient if you have a calculator with you. So we have the flow rate and we have the required flow velocity. We need to calculate the pipe diameter. Basic discharge equation can be used. Okay, so I have got answers as 1.49 and 1.492 meters. Okay, let's see. Yes, approximately it is 1.5 meters. So it's given that flow Q is equal to 3.5 meter cube per second. Flow velocity V is equal to 2 meter per second. So cross-sectional area, in order to determine the diameter of the pipe, we need to determine the cross-sectional area. So we know that flow Q is equal to A into V, that is cross-sectional area into flow velocity. So cross-sectional area is equal to flow or discharge by flow velocity, that is Q by V, which is equal to 3.5 by 2, which is 1.75 meter square. Now we know that cross-sectional area of a pipe is equal to, circular pipe is equal to pi by 4 d square. So rearranging for the diameter, we have d is equal to square root of 4a by pi. Substituting, we have square root of 4 into 1.75 by pi, which is 1.493 or approximately 1.5 meters. Hope that is clear to everyone. So, the next question, question number 13. If the distance from source to reservoir is 1.6 kilometers, frictional head loss in raw water transmission, assuming friction factor as 0.032 is. So we have the same flow here, that is 3 what was it? 3.5 meter cube per second, and the flow velocity 2 meter per second, and the flow velocity 2 meter per second. So if the distance from source to our storage reservoir is 1.6 kilometers, that is if we have to transmit the water over 1.6 kilometer, then what would be the frictional head loss that is happening over this transmission line? They are given friction factor as 0.032. So what will be the head loss that is happening? So I'll wait for another 2 minutes. This is also a simple direct substitution problem. So I'll wait for 2 minutes for the answer in the chat box and then we'll see how to solve it. Okay, so we'll see what is the answer. Um, okay, I've got two answers in the chat box: 6.95, 6.96. Okay, yeah, so approximately it is 7. So it's given that distance from source to reservoir is 1.6 kilometers and friction factor is 0.032. So frictional head loss HL is equal to FLV square by 2GD. So here F is given as 0.032. L is the transmission length which is 1.6 kilometers. So converting it into meters we have 1600. And then velocity, it was given in the earlier problem as 2 meter per second. So the square should be actually within, while putting the brackets I had made a mistake. Okay, so v square by 2 into acceleration due to gravity 9.81 into diameter 1.5. So it is approximately 6.9, it's like 6.96 meters, it's approximately 7 meters. All right, so moving on to the next question. BHP of the pump required, assuming pump efficiency as 75 percentage.
I am unable to see the question.
Oh, 1 second. No, it has changed actually. Is it the same for everyone? Um, I think another person, Vijay or someone can you please tell me whether it is visible or not?
Yes, ma'am. Question is visible. Question 14.
Yeah. So maybe the problem network issue is with your end. I don't know. Just please check that.
Okay.
Yeah.
Okay.
Okay. So BHP of the question number 14 we are looking now. That is BHP of the pump required is to be determined assuming pump efficiency as 75 percentage if the difference in water level of sump and reservoir is 20 meter, ignore minor losses and take specific weight of water gamma as 9.81 kilonewton per meter cube. So we are asked to determine the BHP of the pump. They have given pump efficiency as 75 percentage. Water level difference between sump and reservoir is 20 meter. That is, we need to raise the water from the sump to a height of 20 meter. All the minor losses can be ignored, and the specific weight of water is given as 9.81 kilonewton per meter cube. So, what is the BHP of pump? BHP is nothing but brake horsepower. BHP, brake horsepower. So again, I'll wait for 2 minutes and then we'll see how to solve the problem. Okay. Hmm. Okay, let's see how to solve this. I think I didn't get any answer in the chat box. Okay, fine. So we'll see how to solve this. So the answer is 1657. It's given that pump efficiency is 75 percentage and difference in water level of the sump and reservoir, or the level to which the water is to be raised, is 20 meters, and specific weight of water is 9.81 kilonewton per meter cube. All these values are already given. So ignoring minor losses, BHP of the pump required will be equal to gamma QH by 746, the whole divided by efficiency eta. So total head to be pumped is suction head plus delivery head plus friction losses plus minor losses. But since we are ignoring minor losses, total head over which water is to be pumped is suction head plus delivery head plus friction losses. Now suction head plus delivery head is the water level difference between sump and the reservoir. So it is directly given as 20 meters. And friction losses we had calculated in the previous question as 7 meters. So the total head to be pumped comes to be 27 meters. Now BHP required is gamma QH by 746 divided by eta. So substituting all the values, it becomes 1657 BHP approximately. Hope that's clear to everyone. Moving on to the next question. Identify the correct statements regarding the appropriate location of an intake for water supply. Intake should be located at the downstream of the disposal point of wastewater. Intake should enable water withdrawal during floods as well as dry periods. Intake should be at a considerable distance from the treatment plant to protect water quality. So these are the three statements. Option A, both 1 and 2 are correct. Option B, both 1 and 3 are correct. Option C, both 2 and 3 are correct. Option D, all statements are correct. So it's regarding the appropriate location of intakes. So which all are the correct statements? Okay, so correct answer is option B. Both 2 and 3 are correct. That is, intake should be never located downstream or even in the vicinity of the point of disposal of wastewater. Because then, in the water that we are extracting for water supply, this wastewater will also get mixed up. The second point is that intake should enable water withdrawal during flood as well as dry period. During all throughout the year, we should be able to supply water. So we should be able to extract water. The third thing is that intake should preferably be near the plant so that the conveyance required from the source to treatment plant can be reduced and hence it can be made more economical. So the location of intake should actually be near the treatment plant. It must be located in the purer zone of the source with the least pollution. It should never be located to the downstream or in the vicinity of the point of disposal of wastewater. Site should be able to fulfill water demand at peak levels. That is, it should permit greater withdrawal if required at a future date. Even during the driest period, it should be able to supply water. It should not get destroyed during floods. It should be easily accessible even during flood times. Also, flood water should not get concentrated in the vicinity of the intake. If we are putting it in a navigation channel, It should not interfere with the river traffic. So these are the different factors that are to be considered while fixing the location of intake. So with that, today's discussion questions are over. So I'll stop sharing my screen now. Sorry. Mm, yeah. So if you have any doubts, please unmute yourself and you may please ask. Or else we can conclude the session for today and meet next Tuesday at 7 p.m. Okay, thank you. Okay, then, so we'll close the session for today. We'll meet again during the next live discussion session on next Tuesday. Thank you.